Day 37, Honors Physics, Newton's Three Laws, Example 25. This one's kind of fun because it's a little bit different than the ones we've been doing. So we have to be a little bit more careful about our diagrams here. Are there 7 objects, 1 object? Because as we draw the free body force diagrams, we want to draw 1 object at a time. So how do we do this? Well, in Part A, they're talking about the tension and the coupling. That's right in this area right here. I'm circling it in blue. As the train, the engine is pulling on the car directly behind it. But bottom line is, essentially, if we look at the free body diagram for the sum total of all 6 cars. In other words, we can lump all 6 cars together as one lump mass of 60,000 kilograms. Let me just do that. So together, each one is 10,000 kilograms, a total of 60,000 kilograms of mass. And that mass would weigh 600,000 newtons. Rounding gravity, once again, the acceleration of gravity off to 10. And then the support force would be 600, the normal force, 600,000 newtons. That's really not that important. But what's happening here is that coupling that I circled in blue is providing a force that's pulling that 600,000 kilograms. That's the force we're looking for. They're going to call it T tension. I can call it F or T. Let's call it T. It's the tension, and it's not a rope, but it's a steel connector. But it's pulling 60,000 kilograms. Now, it says, if you read into the problem, or not into it, but just read the problem, it says each of the 6 cars has a frictional resistance of 1,200 newtons. In other words, if you take the 1,200 newtons times 6, which I believe is 7,200 newtons, there's a total resistive force combined for all 6 of those of 7,200 newtons. And the sum mass is accelerating to the right. So in other words, T, I didn't really draw it proportional enough. T should be bigger than the 7,200 newtons. I've got about the same size as far as the length. Don't get too hung up on that. But it's accelerating to the right. So if we apply F net equals ma to that free body diagram I have now for the 60,000 kilogram mass, here's the statement in generic F net equals ma form. But F net here now will be T minus 7,200, the bigger force minus the smaller force, equals the mass, 60,000 kilograms. And it tells you the acceleration is 1.5. So you can solve that now for T. All right, that gives you part A. Now, part B, what you want to do is redraw. I'm out of space here. You could do it at the bottom. I'll do it up here at the top. It says, what's the tension in the coupling pulling the last freight car? So that's back over here, that little coupling right there. So now, all we have to look at is that last car. So if I draw this is part B now. If I simply just draw that last car by itself, it's 10,000 kilograms by itself, which means it's 100,000 newtons in weight, which once again won't matter much, but we want to be thorough here with our free body force diagram. Normal force on that would be 100,000 newtons. All right, and then there's that tension in that. I'm going to call that T2, or actually T6. T6, because that's the tension in the coupling in the 6th car, pulling the 6th car. And that car, we know, by itself has a frictional force of 1,200 newtons, because it's just one car. So F net equals ma for that one will be, I'll do it in blue, F net equals ma will be T sub 6 minus 1,200 equals the mass of that car alone, 10,000, times the same acceleration for everything else, which is 1.5. I don't know if you can see that there. It says 1.5. So the only thing you don't know is t sub 6. So 1.5 times 10,000, so 15,000 plus 1,200 basically to get t sub 6.